Swayam Prabha. Digital India. Educated India.
You can visualize this this setting in this using this picture. So far we have looked at three types of distributions. The first one was the likelihood model, P of x given mu. So in the maximum likelihood approach, we simply maximize the P of x given mu, which gave us the maximum likelihood solution. The maximum likelihood solution is just the point that maximizes the likelihood. Okay? So the optimal solution will be the one where the likelihood is maximized. So this red curve is basically the likelihood function, and the MLE solution will be the maxima of this likelihood function, which is why I've shown that this is the maximum likelihood solution, where the likelihood attains its maxima. On the other hand, when we incorporated the prior information about the parameter, so suppose that our prior, we said that the prior is Gaussian, right? Which is why I have drawn it like a Gaussian. So suppose this green curve is the prior distribution over our parameter, mu. Again, a Gaussian with some mean and some variance, okay? We combined the two distributions, the likelihood and the prior, and the posterior distribution is kind of a compromise. So it's just an intuition of what is going on when we combine the prior with the likelihood. So it's kind of, so the posterior distribution is, we multiplied both these things and normalize it, right? So the posterior distribution is kind of a compromise between these two distributions. And as you can see, the map estimate, right? So what is the map estimate? The map estimate is nothing but the point that maximizes the posterior distribution. So which is basically the maxima of the blue curve. So the blue curve is the posterior distribution of mu. So this is just a simple illustration. You know, I have shown these curves as Gaussians because we are dealing with Gaussians, but in some other problem, these distributions may be some other probability distributions. Okay. So as you can see here, if you look at the green curve, the prior distribution has a mean that is somewhere around this point, right? MLE solution is like here. And as you can see, the map solution is kind of in the middle of the MLE solution and the prior distribution, right? So the prior distribution kind of pulls the estimate towards the prior's mean, because without the prior, we have this as the MLE solution, right? This point. But when we incorporate the prior distribution, then the MLE solution, map solution kind of shifts towards the prior mean. Okay. So we have looked at two approaches. So the first, so in the beginning, we started with a simple loss function approach, right, where we minimize the loss function with respect to the parameter, and we found some solution for mu hat. Then we started with the probabilistic approach, where we started with the likelihood model. We looked at the probability of data given parameters, and then we tried to basically maximize that likelihood with respect to parameter. That gave us the MLE, or maximum likelihood solution. Then we said that we can incorporate prior knowledge about the parameters using the prior distribution, and that gave us the maximum a posteriori, or map solution. Okay? So the map solution is better as compared to the MLE solution because we can now incorporate prior knowledge. Okay? However, both the MLE and map solution have one limitation, that they only provide you a single best estimate of the parameter. Okay? There is no notion of how uncertain or how confident you are about the parameter that you are learning. Okay? So you just get a solution, right? So you don't have an estimate of uncertainty around the parameter that you have estimated, right? So can we get the uncertainty in the parameter? So can we say that, well, mu is the posterior, so mu is close to a mean, some mean, and it has a certain variance, okay? Now that we have a posterior distribution, we can actually answer that question. Because note that we have combined the prior and likelihood, we already have a posterior distribution. But all we did so far is that we only maximize the posterior distribution. But if we can actually compute the full posterior distribution, which is basically this quantity, note that this left-hand side is actually a distribution. Okay? But in the map approach, we only found the maxima of that distribution, right? But and note that finding the maxima did not involve computing the full distribution. Okay? So this point is important to keep in mind, because we are trying to find the maxima of this distribution. And in order to find the maxima, we don't even have to bother about computing this distribution, because we could only deal with the numerator terms and we could find the optima, right? But if we want to go all the way, we can actually compute the denominator also, and we can get the full probability distribution of mu given x, right? Turns out that in some cases, it's actually not all that hard. You can actually get a closed form solution for P of mu given x, which will not only give you the maxima, but the full distribution itself. Okay? So let's look at how we can get that. So first of all, it's important to keep in mind that both MLE and map, they both only give us a single best estimate of the parameter, which is also known as a point estimate, because you're only getting a single point, single optimal point mu. However, as I said, oftentimes we are interested in finding the full posterior full distribution over the parameter given the data. Okay, so can we compute this full distribution? So as we have already seen this definition, this is the likelihood times prior divided by P of x. And this P of x is known as the marginal likelihood. This is nothing but the integral of the above. So note that this is a probability distribution, so this must integrate to 1. Okay, so the denominator is nothing but, so it's basically just the integral of the numerator over all possibilities of mu. Okay, if mu takes only a finite many values, then it's nothing but a summation. Okay. So as I said, if we can somehow get the full posterior distribution, it provides a more holistic view of what the parameter is that we have learned. Okay, rather than just telling you, okay, this is the most likely value of the parameter, we can actually get the full distribution over the parameter. However, it turns out that it's usually a much harder problem than just finding the maxima of the distribution, because if you think of this integral that I was talking about, this integral is not always doable. It's not always easy to compute this integral, okay? Because the forms of these distributions, P of x given mu and P of mu, may be very complicated, and I may not be able to perform this integral in closed form. Okay, so which is why getting the full posterior distribution is in general a much harder problem than finding just the map estimate. However, in certain cases, this integral can be very easily estimated. Okay, and thankfully, the case that we are looking at right now, which is basically the mean of estimating the mean of a Gaussian, there this integral can be performed very, very easily. In fact, you don't even have to perform it. You can kind of guess what this integral will be. As we will, in fact, I will not go through all the details, but I'll just give you the intuition as to how this works, and hopefully that will convey the basic idea. Okay, so as I said, in the case of Gaussian mean estimation, where both these distributions, P of x given mu, what was this distribution? Anyone? P of x given mu? What was this distribution? Gaussian. It was a product of Gaussian, product of n many Gaussians. What was P of mu? Again a Gaussian, right? So in these cases, when the likelihood and the prior are Gaussian distribution, it turns out that the posterior distribution is also a Gaussian distribution. Okay, and you can actually show this in a couple of steps of algebra. But the basic idea is that if the likelihood and prior are Gaussian, then the posterior distribution is also Gaussian, whose mean and variance can be estimated in closed form. I'll just give you the expressions. I'll see if I can provide a basically brief explanation as to why the final expression comes. Okay, anyway, so the posterior distribution in this case will be, again, a Gaussian distribution whose mean will be equal to mu n, which is defined here. So mu n is this expression. And the variance is given by sigma n squared, where sigma n is basically this quantity, 1 by this sum. I'm using the subscript n here to denote that I am computing this posterior distribution, assuming that I have n data points, okay, that I'm using to compute this posterior distribution. Okay. Now, as I said, if I had the, okay, so the basic, it's actually not that hard. I'm avoiding using the stylus on the workspace, but I'll just give you the basic intuition as to how you can get this expression. You should try it at home. It's actually not all that hard. So the basic idea is that, just consider one observation. Suppose n is 1. So I just have, let's say, one data point, x1. Okay? So in that case, I will be multiplying a Gaussian distribution, Gaussian likelihood, and a Gaussian prior. Okay? Both are Gaussian distribution, both have the same expressions, right? Same form of the expressions, right? And what you have to do is that you have to identify the product. So when you multiply two, so you'll have two exp of something times exp of something, and some constants, right? So when you multiply two exps, the exponents will get added up, and then all you have to do is you have to identify the resulting expression as a quadratic function of mu. Like, so you have to identify it as mu minus something squared divided by something else squared. Okay? Because eventually the expression that you are finding, P of mu given x, is a distribution over mu, right? So you can actually see that when you multiply these exps, you can actually massage the final expression, and you can find it as mu minus something squared divided by something. So mu minus that something will be the mean. It will just turn out that it will be this expression precisely. And that divided by something squared will be this sigma n squared. Okay? So if I could access I find it very uncomfortable using the Can someone switch? Let me just try if I can switch. Okay. I'll just try to show you briefly so that those of you for whom it's not clear, hopefully it will be clear. Okay, so I'll just like do a very simple. So note that this is visible, right? So we are trying to estimate P of mu given X. So suppose I only am estimating for one data point, X, okay? So suppose X is just one data point. So what will be this, what will this be equal to? It will be equal to P of X given mu times P of mu divided by P of X, okay? Okay. Okay, so this is what we want to estimate. And we know that P of X given mu is proportional to EXP of minus X minus, you know what, let me just use xn here just to denote that it's the nth data point, okay? So, sorry, I'm bad with the stylus, but okay, so it will be something like this. So the first EXP term will be like this. The second term, P of mu, will be again proportional to EXP of minus mu 0 squared divided by 2 sigma 0 squared. Clear? So this is what we had, right? So the first term is the likelihood of one observation given the parameter mu, which looks like this, EXP of minus this term. P of mu is proportional to this. I'm ignoring the normalization constant in the front because they are not important here. Now, when we want to compute this posterior distribution, I have to first multiply these two terms. When I multiply these two terms, I will get EXP of, so product of these two EXPs, right? So I'll have something like xn minus mu squared divided by 2 sigma squared plus minus mu minus mu 0 squared divided by 2 sigma squared. It's just plain algebra. It's actually not all that hard, but I'm just showing you how you would do this. Okay? So the product will have a term like this. Now, what are we trying to find? So we are trying to find P of mu given xn, right? Now, if you look at this term, if you expand this, you will have terms that will be of form mu squared. So you'll have terms quadratic in mu, right? If you expand this, you'll have xn squared plus mu squared minus 2 xn mu. Here also you'll have mu squared plus mu 0 squared minus 2 mu times mu 0, right? So overall, you will have terms in mu that are only quadratic in mu, and then they will be linear in mu, right? So you'll have something multiplied to, like, so something like mu times b. And you'll have like something a times mu squared plus mu times b. Okay, so this is what you will have. Plus you'll have something like c here. Okay, c will not depend on mu. Okay, now you can always express it as so if you take a out, you'll have something like this, right? And then what you can do, you can write it as mu minus something squared. Okay. Okay, so you can always like so, and then if you can write something as exp of a times mu minus c squared, right? Then c is the mean of the Gaussian distribution, and 1 by a is 2 sigma squared, right? So you can just identify what the mean and variance will be of that Gaussian distribution. Okay, so you can actually so you can do this algebra, and you can find that the final expression will actually have. So I only did it with one data point, but if you have more data points, you'll just have an entire summation here. Okay, so. So anyway, so this is what you will get. So the posterior distribution will be a Gaussian with mean mu n and variance sigma n squared, where mu n is given by this expression and sigma n is given by this expression. Okay, but now note that this is now a full distribution. We are saying that mu, we don't have a single value of mu. We actually have a full distribution over mu. Okay. Of course, from the full distribution, you can get the optimal value. You can say that what is the most likely value? Well, you can say that it's the mean of the Gaussian distribution or mode of the Gaussian distribution. Interestingly, if you look at mu n is the same as the map solution. Okay? So what is mu n here? Mu n is the mean of this Gaussian distribution. What does map give us? Map gives us the mode of the posterior distribution, the maxima. However, for a Gaussian distribution, the mean and mode are the same, right? Which is why mu n is exactly the same as the map estimate, right? But for other distributions, the mode and the mean may not be the same, in which case the map estimate may not coincide with the mean of the posterior distribution. For the simple Gaussian case where Gaussian is symmetric, it just happens to be the same. Yeah, so what I'm saying is that if you look at this solution here, we have obtained a posterior distribution over mu, which is a Gaussian with mean mu n and variance sigma n squared. The mean mu n is equal to this expression, right, that you see. If you recall, the map solution that we obtained last time, right, had the exact same expression, right? However, map gives us the mode of the distribution, the maxima of the distribution, whereas this is just the mean. So mu n is just the mean. However, for a Gaussian, the mean and mode are the same, which is why it's not surprising that we obtained the same expression for both. Okay, right. So what additional information we have when we are finding the full posterior? Well, we don't have a single best estimate. We actually are saying that we have a full posterior distribution over mu, which has both a mean and a variance. So this sigma squared is telling us about the variance or uncertainty that we have about our estimate of mu. Okay. Now pay attention to the form of this variance. So variance, so if we have a large variance, it means that we are quite uncertain about what the estimate is, right? Now, let's again consider the case when n becomes very, very large. What happens to the variance? When n is very large, what happens to the variance of the posterior distribution? It tends to 0, right? Which is kind of expected, because if you have like tons of data, right, you can get a fairly accurate estimate of your parameter, right? You would have very little or almost no uncertainty in that case, okay? So the uncertainty is more intuitive. So this is the intuitive justification as to what happens when we see more and more data, right? So this example kind of shows that as we acquire more and more data, our estimate of the parameters becomes more and more certain. Like initially we have a large degree of uncertainty. If n is like small, then this variance will be fairly large. Okay, so you can imagine that the picture that I showed you on the previous slide, right? So this is the blue curve is the posterior distribution, right? So as you see more and more data, your posterior distribution will keep on shrinking, right? And eventually it will just collapse to the mean or the mode of the distribution. Okay. In the beginning, it will have a fairly spread out posterior distribution, but as you acquire more and more data, this will keep on shrinking, and it will peak. It will basically attain its. It will just collapse or shrink at the mean. So it will have almost 0 variance in that case. Okay. So one thing that I mentioned earlier is that if you recall, if you notice here, what was our prior distribution? It was a Gaussian, right? P of mu was Gaussian, the prior distribution. Our posterior distribution is also a Gaussian here, right? So the prior is the same distribution as the prior. So the posterior is the same distribution as the prior, but of course with the different set of parameters. Okay, both in this case are Gaussian distribution. Okay. This is a very nice property that in some problems, in some parameter estimation problems, the prior and the posterior, they both happen to be the same distributions. Okay, and that happens when the likelihood that we have P of x given mu and the prior, if they both are conjugate, then this happens. So there are certain pairs of distributions where if one distribution is treated as is used as a likelihood and the other distribution is used as a prior, and if they are conjugate distribution, then the posterior also has the same distribution has the same distribution as the prior distribution. So for conjugate pair of distribution, this property holds, and as a matter of fact, Gaussian distribution is conjugate to itself. Okay, so if you have a Gaussian likelihood and a Gaussian prior distribution, then the posterior distribution is also Gaussian. So just for a reference, I have listed some pairs of distributions, and where one of the distribution can be used as a likelihood, the other can be used as a prior, and the posterior will also have the same form as the prior distribution. So if you can see here, I have listed some examples. So if you have a Bernoulli distribution as a likelihood and a beta distribution as a prior, then the posterior happens to be beta distribution. So these are all pairs of conjugate distributions. Okay, if you have binomial likelihood with beta prior distribution, then you again have you get a beta posterior. So if you do this algebra of taking the prior and multiplying with likelihood, and if you compute the posterior, it will be you will just get the same distribution as the prior distribution. So again, multinomial is conjugate with Dirichlet, you again get a Dirichlet posterior. Gaussian, as I mentioned, is conjugate to itself, and in which case you get a Gaussian posterior. I should also mention that Gaussian distribution is also conjugate to something called a gamma distribution if the variance or the mean is known of the Gaussian distribution. Okay, so there are many other pairs of distribution that are known to be conjugate. So if you're doing probabilistic modeling of data, and if you are lucky, you may be working with a likelihood distribution for which there is a conjugate prior, and in which case the posterior distribution computation of the posterior becomes very, very easy, as we have seen in this case. Okay. Okay, so a beta distribution is a distribution over numbers that range from 0 to 1, positive numbers between 0 to 1. So there are many types of distribution. So Gaussian is distribution over real values, right? Minus infinity to infinity. But Bernoulli distribution is distribution over binary numbers, 0 or 1. A beta distribution is a distribution over numbers that range from 0 to 1. Okay. So suppose you're trying, okay, I'll give you an application of where a beta distribution might be used. Okay. So I don't have that example in the slides here, but suppose I'm trying to estimate the bias of a coin. So suppose I have tossed a coin, let's say a number of times, and I want to estimate what the probability of a head is. Okay. I can again do the same things that we did. We can do maximum likelihood estimation. We can just write down the likelihood of the data, right, as a function of the probability of the coin, showing up head, and then I can find the MLE estimate. But if I want to do map estimate, I need a prior distribution on the probability of the coin showing up head. So what would be an appropriate prior? Okay, so I need a prior distribution that that is defined over numbers between 0 and 1, right? So thankfully we have a beta prior, and the nice thing is that beta is actually conjugate to prior distribution. So if you do this coin toss estimation problem in a Bayesian or in a probabilistic way, you can use a beta prior, and you'll be guaranteed to get a beta posterior. It's very simple to. In many textbooks of machine learning, you are given this example as well. Okay. So likewise, a Dirichlet prior is a prior distribution over probability vector. So if you have, let's say, k numbers that sum to 1. So suppose you have you seen Gaussian mixture models in this summer school yet? Not yet. So suppose you're trying to estimate a mixture model where data comes from k distributions, and suppose every distribution has some fraction of points allocated to it, right? And so the fractions sum to 1, right? And you don't know what the fractions are, right? So you are trying to estimate a probability vector. Okay. So on that kind of a vector, if you are doing a probabilistic modeling, using a probabilistic modeling approach, you need a prior distribution. So Dirichlet is a distribution over probability vectors. Okay. So again, we'll not get into the details of those. So likewise, there are many pairs of distributions that are conjugate to each other. So Poisson is conjugate to gamma. You again get a gamma posterior. So in fact, it's kind of beyond the scope of this lecture, but so there is a class of distributions known as exponential family distributions. So every distribution in an exponential family has a conjugate prior. So if you just look up Wikipedia, you can actually just search for exponential family distributions, and you'll get a list of basically distribution. So in fact, all these distributions are from that family, which is why they all have conjugate distributions. But that's something that we are not going to talk about today. Okay? Right. And I should also mention that it's very easy to identify if two distributions are conjugate to each other. So in fact, if you just look at the functional form of two distributions, if the form looks similar, for example, if you look at the Bernoulli distribution looks something like this. It looks like theta to the x, 1 minus theta to the power 1 minus x. Theta is the parameter of the Bernoulli. Okay. Likewise, a beta distribution looks like theta to the power alpha minus 1 times 1 minus theta to the power beta minus 1. Now, as I mentioned in the very first line, beta and Bernoulli are conjugate to each other. And if you look at the expressions, they look quite similar. Theta to the power something, 1 minus theta to the power something else. Okay, in both cases. Which is why when we do posterior estimation, in posterior estimation, what we do, we take the likelihood multiplied by the prior. So note that if I multiply these two Bernoulli and betas, we'll have theta to the power something plus something. Theta to the power 1 minus theta to the power something plus something, right? So again, the final result is a beta distribution, right? Which is why conjugate distributions are very easy to play with. Okay. All right. So we have seen three approaches for parameter estimation using probabilistic models, right? So the first approach was that you write down the probability of data given the parameters, which is also known as likelihood, and you just maximize the likelihood with respect to parameters. That will give you the maximum likelihood approach estimation. You can also incorporate a prior distribution, in which case you can actually do the map estimation, where you simply find the parameter that maximizes the posterior probability, right? And the third approach is that you can take the full base, you can infer the full distribution, where you can get not only a single point, but the full distribution over the parameter, along with the variance. Okay. Okay. So any other questions before we move on? Okay. So we have seen that we can estimate parameters taking a probabilistic approach, where we formulate the modeling problem as something where the data is being generated from some probability distribution, and we may have some prior distribution over the parameters, and then we can combine these two quantities to get the posterior distribution or the maxima of the posterior distribution. And the good thing about this approach is that if you have little amount of data, then it becomes even more useful, because then you can incorporate your prior knowledge about the parameters in the estimation problem. Yes.
The input is text.
Yes.
Which type of distribution?
Yeah, so good question. So it depends on how you are representing the text, okay? So if you are representing the text as, let's say, bag of words, okay, in which case you can use something like a multinomial distribution, okay? If you are thinking of the input as bag of counts, basically, so like in a text document, how many times a word is occurring, each word is occurring, right? You can use something like a Poisson distribution, which is count. So again, it depends on how you are representing the text, okay? So things like so you basically have some discrete distribution, like multinomial or Poisson distribution. Okay, so we have so far seen how to estimate parameters, but that's not the only task that we care about. Often in machine learning, we care about making predictions. We have some data, we have learned some parameters, and then we are going to predict something, right, about future, okay? So in this simple problem that we are looking at, where we are just trying to estimate the mean of a Gaussian distribution, right, what might be a prediction task, okay? So the prediction task, one prediction task could be, so this problem of estimating the mean of the Gaussian is also sort of a density estimation problem. So we have some data assumed to be generated from some distribution. And when we are learning the mean, we are essentially learning the distribution, right? Probability distribution or probability density of the data, okay? So once we have estimated the density of the data or distribution of the data, I can ask this question that, suppose I give you a new observation, let's say X star. What is the probability of that observation, given that we have already seen a bunch of so how likely is this observation, given that we have already seen a bunch of other observations from the same distribution, right? So this can be thought of as a prediction task, okay? So intuitively, if suppose I already have seen these X observations, X1 through Xn, and I want to see whether this new observation comes from the same distribution or not. Okay, so if P of X star given X has a, let's say, high value, then it kind of tells us that X star comes from the same distribution, okay? Whereas if P of X star given X has a low value, it kind of means that X star comes from, let's say, probably a different type of distribution. It's an outlier. It doesn't belong to the same, distribution, okay? So this is a very simple kind of a task that, we can formulate for this Gaussian mean estimation problem. Okay, so let's think of this as our prediction task. Okay, so we can think of P of X star given X as our predictive distribution. Like, having seen capital X, which is X1 through Xn, what is the probability distribution or probability density of X star given the previous observations? Okay. Now we can solve this task. We can compute this predictive distribution using any of the approaches that we have taken so far. So we have looked at MLE estimate, map estimate, or the full posterior distribution, right? So if we have MLE, what would this be equal to? If we have map estimate of mu, what will this be equal to? Or if we have the full posterior distribution, then what will this be equal to? Okay? So depending on the kind of estimate you have, you can get different answers to this problem, to this question. Okay? So let's look at what, but note that both MLE and map, we get a single mu, right? Whereas in the second case, we get a full distribution over mu. Okay? And suppose our task is to compute P of X star given X. Okay? Now this can be done in two ways broadly. In the first case, we can compute, so this is also known as a predictive, so this is a generic kind of a term that I'm using. So predictive distribution is something that you're trying to predict something about a new observation given the previous observations, right? Which is why I'm calling it a predictive distribution. Now, there are two types of predictive distributions that you can compute depending on what kind of estimate you have for the parameters that you have learned. Okay? So the first approach is known as plug-in predictive distribution, and that is used when you only have a point estimate of the parameter. So if you have MLE or map estimate where you only get a single mu hat, you can use a plug-in predictive distribution, in which case you can say that P of X star given X is approximately equal to P of X star given the plug-in estimate of mu. Okay? Because if I have mu hat, I know that, so what is this distribution? This is like, this P of X star given X is a Gaussian with mean mu hat, okay? So if I only have a single mu hat, this will be our plug-in predictive estimate. I'm simply using the single estimate of mu that I have, and this is, in our problem that we have, this is nothing but a Gaussian distribution with mean mu hat that we have estimated. The second way of computing this predictive distribution is called a posterior predictive distribution, where you average over all possible values of mu. Okay, because in this case, we are only relying on one mu, right? We are simply saying that let's approximate it by a Gaussian with mean mu equal to mu hat. Okay. However, if we have a full distribution over mu, which is the case when we have a full posterior distribution, we can actually compute this quantity by averaging this thing over all possibilities of mu. And by that, what I mean is that I can write P of x star given x as, okay, so this is a simple sum rule of probability. So I can write this quantity as the joint distribution of x star comma mu with mu summed over. Okay, so this is just the sum rule of probability, right? So this marginal distribution of x star is the marginalization or summing over of the joint distribution of x star and mu. And this joint distribution can be written in by, so you can use chain rule and you can split it as P of x star given mu times P of mu, right? Or mu given x, right? So note this form, right? Okay, and finally, so this is the joint distribution. This is, we have used the chain rule to split into two parts, and then the first part, P of x star given mu comma x. Note that if I'm given mu, then the probability of x star does not depend on x, because x's are IID. All the observations are IID. So this first term can be just like written as P of x star given mu. Okay. So pay attention to this red expression in red. So what it is saying is that the predictive distribution is an integral, or think of it as a summation if integrals bother you. Okay. So it's an integral of this predictive density of x star given a single value of mu times the posterior probability of mu, and then you are averaging over all possibilities of mu. So essentially, rather than sticking to a single value of mu, you are considering all possible values and integrating or averaging over all possibilities. Okay? As opposed to the previous case. So in the previous case, note that I'm simply using a single mu hat to compute P of x star. Okay? P of x star given mu hat. But here I'm using P of x given mu, and I'm multiplying it by the posterior probability of that mu. So it's kind of posterior weighted average. So I'm computing this probability, I'm weighting it by the how important, so because what is this quantity equal to? So this quantity is like how important this a given mu is, P of mu. So if some mu is more likely under the posterior, then this quantity will be high, right? So essentially in this case, how many possible values mu can take? Infinite many values, right? Mu is a continuous, it's a Gaussian distribution, right? So essentially, I'm considering all possible, like infinite many values of mu. I'm computing this probability for every mu, and then I'm averaging over all possible. I'm multiplying each. So this is like a prediction, right? I'm weighting this prediction by the posterior probability, which is like how important that mu is, and then basically I'm just summing over all possibilities, right? Right? So rather than relying on a single mu, I'm just averaging over all possibilities of mu. So which is why this is also known as posterior averaging. Okay? And this is a drastic difference. So this is a significant departure from this other approach where we are only relying on a single best, right? So this is kind of like a more robust approach, right? We are saying that, well, we don't trust a single value of mu, right? So which is why we will just average over all possibilities of mu. Of course, we will not weigh every possibility equally because we have this okay. So we have this posterior weighted version. Okay. So this is known as the posterior predictive distribution. In the previous case, if we are only, okay, so this is the key difference between, so there are two types of predictive distributions. Once you have learned the parameters, if you are only using a plug-in estimate, then you call it a plug-in posterior. If you are using the whole posterior distribution to make the prediction, then you call it a posterior predictive distribution. This distinction is important because this is something that we will look at in the second lecture also when we talk about linear regression. Because suppose, I'll give you a picture that illustrates this idea as to what happens when we do the averaging. So as I said, averaging is more robust because you're saying that, well, I don't trust a single estimate of mu because it might be as a result of overfitting, right? So rather than trusting a single estimate, let's just average over all possibilities of mu. Okay, that we have from the posterior distribution. Okay. Yes, indeed. So this is indeed computationally expensive. However, again, in some cases, the form of these distributions enables us to get a closed form expression. So you don't actually have to do this integral numerically. So in some cases, you can just so suppose if this is Gaussian, this is Gaussian. So in fact, for this problem of Gaussian mean estimation, P of x given mu is Gaussian, right? Likelihood model is Gaussian. our posterior is also Gaussian. So when we multiply two Gaussians and integrate, if they are in this form, we actually get another Gaussian. So we don't actually have to do this integral explicitly. Other cases, we actually have to use numerical approximations. Okay, so the whole area of Bayesian machine learning is actually about using those approximations. But if we are lucky, we can actually get close to them. I'm not sure if I have an expression for this in this slide, but I might have it in some of the later slides. So it's actually very simple. This expression has a very simple analytic form. So as I was mentioning, so this posterior averaged version of the prediction is usually more robust because we are not relying on a single value of the parameter, but rather we are using the whole distribution, right? But as someone pointed out, this is also much harder to compute as compared to the plug-in prediction. Okay? So if you think of probabilistic modeling, when it comes to prediction, so first of all, there are two type of tasks, right? One task is parameter estimation. There we can either do a point estimation using MLE map or estimate a full distribution, okay? In the second case, when the second step is when we make predictions. So there also we have two choices, right? Either we use a plug-in estimate, in which case we can just compute a plug-in predictive, or we can use the full information, all the information in the posterior, and we can compute the posterior predictive distribution. But the latter is definitely harder. In general, it is harder, but in some cases, it can be done tractably. Any other questions on this? Okay.